Okie dokie, okie dokie, okie dokie. So, part two. Let's get rolling on part two. Before we get into part two, guys. Before we get too far into part two, let's back up a second and just talk about acids and bases again. Would you be more concerned about a strong acid or a weak acid? I heard that was like a mixed response. I was expecting people to say just strong, but I heard it was weak, possibly. Like you thought it was a trick question. Not intended to be a trick question. The higher the Ka value, the more dangerous, right? And that's where you primarily focus. When we get into our second half of this chapter, the second half of this topic, we might have two acids. Do you care about the one with the higher Ka or the lower Ka? Higher Ka is going to donate more hydrogen, so it's going to control the pH. The second one, the weaker one, is going to donate less, and you can add that hydrogen on, but quite often the second one is donating like 1/100th of a hydrogen by comparison. It's just like 100 times smaller. Yes, sir, in the corner.
So hydrofluoric is a weak acid.
Hydrofluoric is not on the list of really strong acids, right? And it's not on there. This is my understanding why it's not on there. Hydrofluoric, you got a hydrogen and a fluorine. Fluorine's really electronegative. What element is usually pulling the hydrogen off of the anion? Oxygen. The water and the oxygen in the water, said that backwards, is usually the one coming over and pulling the hydrogen off of whatever anion it's attached to. In this one case, the anion is stronger than oxygen. And all the other halogens, fluorine and chlorine, chlorine, bromine, iodine, and the 5 astatine atoms on the planet, they're all halogens, and when they have hydrogen on them, the oxygen is stronger than them and can pull the hydrogen off most of the time. So that's the only acid in the halogen family, HF, that is considered a weak acid. And it's a weak acid because fluorine is stronger than the thing that's trying to pull the hydrogen off. Fluorine itself is extremely corrosive, right? I had a question in my other AP Chem class about why does some acid dissolve zinc but not copper, and some dissolve copper but not lead, and it can't be the hydrogen then, is it? Because every acid has the same thing. They have hydrogen. It becomes the anion. Whatever the anion is must be reacting with that metal, with that substance, in a different way. And if they're different anions, shouldn't they react differently? Right. So like hydrofluoric acid is extremely corrosive to tissue. Extremely corrosive. So you don't want to expose your tissue to... We're not even allowed to buy hydrofluoric acid. It's so corrosive. Whereas we're allowed to buy sulfuric, nitric. Nitric eats copper. Like, we have to have we have a whole separate cabinet just for nitric acid. And then we have another cabinet with all of the other acids in it, if they're in aqueous form. So there's two aspects to every acid, the hydrogen and the anion. And so, good? So I'm going to just briefly talk, like we have an acid, and it reacts with water, and it produces what? What do we call this thing? This is hydronium. And then there's the anion. If we have a base, the general base reaction looks like this, where B is going to be taking a hydrogen off and producing hydroxide. And if we're measuring pH, we're taking the negative log of hydronium. If we're measuring pOH, we're taking the negative log of hydroxide after the reaction occurs. That's what we're taking the negative log of. How much hydronium or how much hydroxide is in the solution. That was kind of what we were hitting at near the end, but I know that when you get to like hour 75 of the homework review, you're like, So I thought I would just bring that back up because that's kind of one of the key points. We're not really measuring how much is on this side. because on this side, the hydrogen's not free. On this side, it's still attached to the anion. We're measuring how much is free. With strong acids, how much hydrogen is free? All of it, right. The Ka is so huge that really it just all goes this direction. Just all of it. And so what you can do with the strong acids is very different than a weak acid, is you could say, hey, if this is 5 molar, then actually this is 5 molar if it's a strong acid. If it's a weak acid, that's not the case. If this is 5 molar, you might lose 1% of it, and so this is like 0.05 molar, and then you take the negative log of that to get your pH. You have to be given some information to figure it out. We were using rice tables to figure it out a lot, weren't we? You don't have to use a rice table because generally it's minus x on the left side. Both of these are plus x on the product side. So you end up with x squared over your initial value minus x. And typically x is so small it's just the initial value. Then you're given some hints like how far did it dissociate. They tell you the percent dissociation. That tells you x. Or they tell you the pH. If they tell you the pH, what can you figure out? You can figure out the amount of hydronium. And if you know the amount of hydronium, you know the X value, and you can fill in a lot of gaps in there. On the flip side, let's actually just delete all of this. What if you just put the anion in water? So you make some sort of salt. You put like Ka in water, where K is a... No, wait. There we go. Put your mom in water. M stands for metal, A stands for anion. Okay? So you put this metal and the anion in water. The anion might react with water and behave kind of like a base, take a hydrogen off, and free hydroxide. The metal, well, the metal's got a positive charge. What could it do? What could it take from the water? OH. It could take the OH and produce hydrogen ions. And so depending on the strength of these two things, one of them is going to be better at this. Whichever one's better at this is going to determine the pH. Just like if you have two acids and the one that's stronger is the one that determines the pH, if you have two anions going into water, the one that's stronger determines the pH. But there's a third substance in water that I often ignore, and that's the water itself. It's real easy to forget that there's water in water, and that sounds really stupid. But does water have a pH? Does it make hydrogen ions? Does it make hydroxide ions? Very tiny quantities, but let's just write this stupid reaction. Water plus water makes hydronium and hydroxide. Now, if you've got regular boring water at room temperature, the reaction ends up at 1 times 10 to the minus 7 and 1 times 10 to the minus 7. And so the pH is 7, or the POH is 7. There is a third scenario. Austin puts this anion and this metal into water. They're both really weak. And the strongest thing in water is the water. You got that weird third scenario? So I accidentally did a demonstration in my other class with a sulfate, where I put sulfate into water, and sulfate pulls hydrogen ions out and the pH just barely goes up. And I was a little bit off as why didn't it change more? Because the water was actually still the strongest thing. And the amount of hydroxide or hydronium that was being made was insignificant compared to the amount that water makes all by itself. So it was 1 times 10 to the minus 7 plus 1 times 10 to the minus 6, which made it like 1.1. So it clicked the pH up to like 7.8 or something like that. It wasn't a huge change. So that's kind of what we're going to be dealing with, though, in this second half, is how do these anions behave? And one of the key things was realizing, or looking at this new equation, that the equilibrium constant for an acid and the equilibrium constant for its conjugate base are related. And this is the acid and conjugate base pair, or it's the base and its conjugate acid pair. So if you know, I'm a little too zoomed in, aren't I? If you know the conjugate acid and you know the base, let's just pick one, hypochlorous. Here we go. If the acid is HOCl, what is its conjugate base? OCl minus 1, right? Because it's losing that hydrogen. And since recording my singing, that's weird. Since we know this is 3.5 times 10 to the minus 8, we could figure out what OCl would be. We would just plug the Ka for HOCl, and that's called hypochlorite. So we could figure out the Kb for hypochlorite just by doing some division. Let me pick up my calculator because I don't have this pre-done. Shame on me. .8 times 10 to the minus 7. Technically 2.9. There we go. That doesn't look any different, does it? So 2.9 times 10 to the minus 7. If you put a salt, a metal with OCl into water, the OCl would behave like a base. And it will take hydrogen, and you can use this value to calculate how much hydrogen it can take. You got me? You'll use that value for OCl. That's the reaction that's going to occur in there. And we already went over everything that's sitting up here on the board, so I'm gonna like use my giant eraser and just create a new problem here. So we could say, hey, you put sodium hypochlorite into water. What's the hypochlorite going to do in the water? It's going to take some hydrogen off and make some hydroxide. Give me a molarity. I always go to you. What's your random number of the day? That's really precise. 3.114. I was sure you were going to go 315 because it's the date, but no. You disappointed me. And so this is the molarity, 3.114, of NaOCl that he's made in water, and the OCLs might react with the water. Some quantity of this is going to disappear as this appears. And we could solve for that. We could say x squared over 3.114 equals my Kb, 2.9 times 10 to the minus 7. And where'd my minus x go? I'm assuming it's insignificant. Blah, blah, blah. I'm assuming it's, let's just say, too small. It's so small that I can ignore it. And so I'm going to cross multiply and solve for x. Oh, that number's still in my calculator. That's nice. And take a square root. Oh, it is pretty small. So x equals 9.4 times 10 to the minus 4th. Is that small enough to ignore it? That's really small. So it's okay for me to ignore it. So then I can, if I take the negative log of that, what will I be calculating in terms of pH or POH? Which one will I be calculating? The POH. Because this is x, and x represents how much hydroxide is in water. This is an acid, but this isn't free hydrogen. This acid's not free. It's attached to the OCl. So I'm going to measure how much hydroxide's in the water. And my POH is 3. So what's my pH? pH would be 11 because it adds up to 14. So that's pretty basic, isn't it? And by no means easy, which I think is one of the most evil terms about the concept behind the word basic. Is you feel like you're supposed to understand it, even though it's pretty complex. When I took intro freshman chem in college, I did not understand this at all. It really kind of threw me for a loop because I was so used to that one thought, that the Arrhenius definition of acids and bases. Acids give hydrogen, acids give hydroxide. That's for really simple acids and bases. But when we get to salts, ionic compounds dissolved in water, we often miss that the salt might react with water, and that's what's going on here. And that's like the second half of this chapter, is that the salt might react also. All right? And that's what's going on again and again and again, and the rest of these problems is we're supposed to think about how it might react. I'm not going to record all of the steps because otherwise the video will be 45 minutes long. We're going to pause, work them out, come back to recording. Sound good? All right. Like the people at home have any choice. So my maniacal laugh may have been a little premature. You missed a good moment, so I'm going to have to re-record it all. It's not going to go as well as it just did. Sorry, people at home. Hey, ladies here in the classroom and gentlemen. So what we've done so far is we've said, hey, so this has two parts. There's a cation and an anion. And we need to think about who their opposites would be. So the opposite of Cl is HCl. That's its conjugate. And the opposite of whatever the heck this is, does anyone know what that's called? No. This one down here, the CH3N28, that's methylamine. But I don't know the name of that one. I just don't. Let's just call it methylammonia. I don't think that's quite right, but is that what you said back there, you in the striped shirt? Yeah, some guy in a striped shirt said that. So the way I kind of look at this is, think about who's the strongest. It's hard to identify who's the strongest sometimes, but if you can identify who's the weakest, you know the opposite's the strong. So let's look at the first pairing, the pairing we know most about. This pairing right here. Who is stronger, chlorine or HCl? HCl is one of the strongest acids. And if you're a really strong acid, your conjugate is really weak. So what's the Ka of HCl? It's like infinity or something. So if its Ka is infinity, then Cl's Kb, remember they're tied together by that little equation we were looking at, Cl's Kb would be 1 divided by infinity, which as far as I understand in mathematics is basically 0. So Kb for this thing's Kb is just about equal to 0. That makes it a really pathetic base. Cl is really bad at stealing hydrogen. Super bad. Which was kind of an iffy movie. But that means instead I need to focus on the other component, because we're primarily concerned with what is the strongest acid or the strongest base. All of our math is really based upon that perspective, because the other thing is so weak it's not going to impact the pH. So I'm going to have to do this entire equation from that compound's perspective. Did I do okay in the re-explain? Yeah, they all just nodded, except for that guy. He just looked at me like, no, that was pathetic. He's always disappointed in me, though. I'm used to it. So I need to find the right K value. Do you see it? There it is right there. Methylamine in its opposite. Oh, I forgot that's a plus up there. That's the plus. There's no charge here. Chlorine's a minus. That's a plus. I messed that up. So let me write that reaction. CH3NH2 would react with water to produce this methylamine stuff, CH3NH3. Strike that, right? Yes. And what else? It's taking a hydrogen. What's the other piece? OH. So now that I've gone through this layer of logic to figure out which reaction to work with, now I can set up the problem. Point 1, minus 0.1 minus x, 0 plus x, 0 plus x. Hey, Mr. Murphy, is it okay if we don't actually write all this rice table stuff and we just skip to the next step? Yeah, that's perfectly fine. I'm still doing it to just kind of hammer it in your head. But by the time you get to the test, most people will just be like, x squared over 0.1 minus tiny x is equal to, what's it going to be equal to? Is it equal to the KB or the KA for this thing? Is this being an acid or is this being a base? It's currently being a base. So it should be the KB. This should be the KB. It's behaving like a base. So I need that value before I can even solve. I have that value right here. Sweet. What if I didn't have that value? What if I had the opposite value? I could just do Ka divided 1 times 10 to the minus 14 divided by Ka. Give me the Kb. So I know the Kb according to this data table here. And now I can solve. So x squared, we're going to make the assumption that x is so tiny, it's okay to do this. I used the wrong one. This is why you should never do things live. Excuse me. Is that the right one? Thank you. And therefore, x squared equals 4.38 times 10 to the minus fifth, because I just multiplied by 0.1. Take a square root. Take a square root. And I'll come back to you people at home in a minute. All right, game on. So x equaled 6.6 times 10 to the minus third. It kept going. There were more values. I didn't actually delete the other values in my calculator. I'm using all of them in my calculator until I'm all done. X represents the amount of hydroxide. So if I take the negative log of x, I've got a POH, which I then converted to a pH. The final answer for part A and number 2 was 11.82. There's a lot of thinking that just went on, wasn't there? It wasn't just a, take the negative log and you're done. That's why these are so much harder. There was a lot of logic in the very first step. Who's stronger, chlorine or methylamide? And it turned out that methylamine was stronger, so then I had to work the problem with methylamine, and I just set the chlorine aside and ignored it. Same thing's going to occur with the next one. Who do you think is going to be stronger, sodium or cyanide? What is the opposite of sodium? NaOH. That is a very strong base, isn't it? So sodium is not going to be the one we work with. It's going to be the cyanide. And its opposite is hydrocyanic acid. And hydrocyanic acid, look at this. That's its Ka. 6.2 times 10 to the minus 10. Is that a strong acid? No, that's a very weak acid. That's a very weak acid. So its Kb is actually going to be pretty big. We're going to have to work that problem with that. I'm going to pause, and you guys at home are just going to see the answer appear in a couple minutes. So deal with that. Alrighty, all those numbers just magically appeared for those of you at home. Let's just run through what just happened. I said Cn makes HCN. HCN is a very weak acid. Its Ka is in that data table right there. Its Ka is 10 to the minus 10. That's pretty weak. Na ions, sodium ions, could make hydroxide, sodium hydroxide, which is a really strong base. Since it's a strong base, you're not going to have much of that in solution. It's going to shift right back and make sodium. So we're not going to worry about the sodium ions because they're not going to really react much with the water. We're going to worry about the cyanide ions. And the cyanide ions, here's the reaction here. The cyanide ions are going to steal water's hydrogen, make hydrocyanic acid and hydroxide. I don't have a Kb though. I had a Ka in that data table. So I said, hey, 1 times 10 to the minus 14th divided by the constant for the acid would give me my Kb. And then I set up Kb equals x squared over 0.05 minus x. I assumed that x was negligible and ignored it right there. I'm still writing minus tiny x. I should have done a test to see if it was less than 5%, but I didn't. I solved for x. I got 8.98 times 10 to the minus fourth. Calculated the pH. Sorry. When I solved for x, I got hydroxide. I calculated the pOH, and the pH would be 10. So what's weird? If I put sodium cyanide into water, what happens to the pH if I create that molarity? It goes up. So you can put a salt into water, an ionic compound into water, and watch the pH change, because the salt is stealing hydrogen from the water, freeing hydroxide. Or, in a couple of cases, the metal ion could steal hydroxide from the water and free up hydrogen. On that side, we haven't seen one like this yet, but quite often, some metal ions and hydroxide are insoluble. Right? Sometimes you put a metal into water, and it reacts with the water and steals the hydroxide. I'm going to pick up my lime water bottle. Remember this lab we did with calcium hydroxide? So if you put calcium acetate into water, if you put calcium nitrate or calcium chloride into water, it'll start to dissolve, but then the calcium will meet the hydroxides that are floating around in water and precipitate out. And as the hydroxides precipitate out with the calcium, they're going to leave what ion behind that changes the pH? As the hydroxides leave, what's left behind? The hydrogens. And so you'd have an increase in hydrogens, which means the pH becomes acidic, because the hydroxides are precipitating out. So that sometimes happens with insoluble metal ions. Metallic ions. Okay. Well, metal ions, metallic ions, it's the same thing. All right, let me pause as we go forward here. So we're going to ignore the sodium, and here's why. The sodium's going to take hydroxide and make sodium hydroxide. Sodium hydroxide is a super strong base. So which way is the reaction going to go if sodium hydroxide is produced? It's going to go back to the left, very strongly to the left, because that has a super big Kb. NaOH does. If NaOH is Kb is huge, then what is the deal with this thing? It's really tiny, right? So it's going to shift that direction and primarily leave sodium ions just in the water. So we can ignore the Batman stuff, because the sodium ions don't produce enough hydroxide to impact sodium hydroxide. Any sodium hydroxide that gets produced immediately dissociates and reverses. It is producing hydrogen, so yes, yeah. Through the reaction, by stealing the hydroxide, it's producing hydrogen ions, so you could look at it as a weak acid, yes. Super duper weak acid, because its conjugate is ridiculously strong. The only thing with that is sodium's more like a conjugate of an Arrhenius. It's more in the Arrhenius world, sodium hydroxide, than the Bronzer-Lowry. So we're ignoring sodium in all of these solutions, and what we're going to try to find is a K value from this data. If we find the K value, we can identify the acid. This sounds like a forensics experiment, to be honest with you. Like, you know, something's just been burned by salt. You've just spilled a salt on your skin, and it's burning you. And I don't usually worry about when I get solids on my skin and then burning me, but they will, because there's water in your skin, and they could react with your skin. And if the anion is powerful enough, it could be a bad day. So here we go. We write the rice table, even though it's kind of a waste of time, because we're going to take this data and throw it into how does the base behave. I primarily wrote the reaction just so my head would be screwed on correctly for the question, that the anion, whatever it is going to steal hydrogens from the water, make a conjugate acid, and make hydroxide. So then I wrote my Kb expression, Kb equals x squared over 0.1 minus x. And then we had this realization as a group, while you at home were just watching a paused screen, that we could use the pH to find the pOH and then take the antilog of that, and we would know hydroxide. And hydroxide represents X. So once I know the hydroxide value, I could plug that in everywhere X is. And if you want to do 0.1 minus X, feel free. It comes out to like 0.9999999, and then you round up to 0.1. Sorry, 0.09999999, and then you round up. So I just left it as 0.1. And I solved for the Kb. This is the Kb for that anion, for whatever anion we have. Is it OCl? Is it Cl? Is it F? Is it C2H3O2? Is it cyanide? That's the question. And then I looked down at my data tables, and none of those anions were given. And I got irritated. But then I realized, if I know the Kb for the anion, could I solve for the Ka for my anion? Because these two are tied together. Kb and Ka are tied together by that adorably tiny little equation where Kw is 1 times 10 to the minus 14. So I solve for the Ka. Which anion is it? Yep, we look down there. We've got a match. So it's the fluorine, which is the anion for HF, that is attached to sodium. It's the fluorine, it's this one here, sodium and fluorine. Cool? Little weird, pretty complex ideas, right? This is honestly one of the hardest concepts we deal with all year long. It is. I'm not going to lie. It's one of the hardest ones for me. I'm better at thermodynamics than I am in this. I just kind of struggle with, which equation? Should I be writing a base equation? Should I be writing an acid equation? And I have to look at what's reacting. Is it a cation or an anion? Anion's going to steal hydrogen. Cation's going to steal hydroxide. I kind of struggle with all that. And the struggle is real, but learning involves struggle. So, true learning does. That wasn't very deep. Anyway, all right, next page. More of the same. Sodium and B. I actually just want to pause and kind of shoot forward a little bit. How would we figure this out? We look at the strength of the two things and figure out, is the cation stronger or is the anion stronger? Who's going to do a better job at pulling hydrogens to them or pulling hydroxide off? And you split it in half. Sometimes it's hard to find where the half is. In the left side versus the right side, the cation versus the anion. We've hit nana a couple times. Sodium, we've gotten pretty good at realizing that group 1 metals, their conjugates are hydroxides. They're, potassium hydroxide, sodium hydroxide. So this side's really weak. The other side might be stronger. What, however, is the conjugate of NO3? What's the HNO3? HNO3 is also a super strong acid, isn't it? HNO3 is one of the strong ones, right? It eats pennies, it's so strong. That's what it has for breakfast. So, if HNO3 is really strong, NO3 must be really weak. What? Yeah? Weak. Oh, I thought you said what. So, this case here, we've got sodium, whose conjugate is super strong, and we've got nitrate, whose conjugate is super strong. So these are both super weak. The strongest thing in the solution is going to be water. What's the pH of the strongest thing is water? 7. It's going to be neutral. The strongest thing in there is just going to be water. Because these both have conjugates that are very strong acids or bases. They themselves are super weak, and the water's the strongest thing we need to worry about. In B, we've got sodium again. Is sodium going to be a strong acid or base? Its conjugate is a very strong base, so it's going to be incredibly weak. However, nitrite, what's the conjugate of nitrite? Nitrous acid, HNO2. That is on this chart somewhere. HNO2, I'll make that bigger so you can actually see it. Times 10 to the minus 4. Not considered a strong acid. So, nitrite is going to steal some hydrogens. The nitrite is going to steal some hydrogens. Make nitrous acid and hydroxide. Is the pH going to go basic or acidic when the sodium nitrite dissolves into the water? The nitrite's going to go into the water, steal some hydrogens, free some hydroxides, so the pH is going to become basic. C. We've got whatever C5H5NH blah 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 is, and then we've got ClO4. I don't know what that is, so its conjugate must be weak, right? That logic decent? The list of strong is pretty well known. The list of unknown is huge. This one, what is the opposite of ClO4? HClO4, which is the strongest acid that you can store. So it's the strongest acid. That means that ClO4 itself is really, really weak, isn't it? So this is a scenario where the C5H5NH is going to react with water. If this is the part that's the base, this is the part that would be the acid. So I need to give a hydrogen away and make H3O. And when I give a hydrogen away, I got to subtract one of these hydrogens. Which one might be the best hydrogen to take off just from a formula perspective? The one with the N, yeah. I've taken that one hydrogen off, and then the charge drops. Oh, it is actually a +1 right here. I forgot that. Let me just. Oh, wow, that's a huge eraser. So there's a positive charge on there, because this would be the positive ion, and that would be the negative ion in the compound. So this is freeing hydronium. What happens to the pH if there's now hydronium in the water? Goes down, and now the solution would be acidic. You kind of getting a sense of how this works? All right. And the next one, we have that nitrate again, which we've already said that the opposite of nitrate is HNO3. And this is that NH4, really? The opposite of NH4 would be NH3, which is not a strong base. It's also weak. So this is one of those neutral scenarios. And we already looked at sodium in OCl. Would potassium and OCl be any different? Why would potassium and sodium behave the same? Yeah, they're both alkali metals. So you could have lithium, sodium, potassium, rubidium, or even a sprinkling of cesium. Any one of those are going to behave pretty much the same. So we don't really worry about KOH. That's a super strong base, so it's going to stay as K ions. But this is going to make hypochlorous acid. And in the production of hypochlorous acid, it's going to free hydroxides. And so the solution is going to become somewhat basic. Yeah. I'm pausing that. See if there's any questions. So D, we're having a conversation without you all at home. D, the question's about the NH3 and the NH4. Yeah, this reaction is going to occur. NH4, water, you're going to make some of this, what's called ammonia here, right? Ammonium is going to react with water and make ammonia. The question is there enough to change the pH? And there's going to be a very minimal amount that shifts. And water will actually be the strongest thing in there. Water just producing hydrogonium and hydroxide. This is going to shift a tiny amount that way and make a little bit of hydronium. Since the Ka is so small, it's not going to shift very far. So if one is strong, then the other is very weak. But if we know neither of them are on the strong list, neither NH4 or NH3 are on the strong list, so they're both very weak. They're balanced each other out perfectly. That's one of the weird things about this. If you have a Ka that's close to infinity, then the Kb would be 1 divided by infinity, right? Pretty much. 1 times 10 to the minus 14 divided by infinity is still that. However, if your Ka is 10 to the minus 6th, then the Kb is 10 to the minus 8th. And what is water? It's 10 to the minus 7. So they're all right in the same realm, and the pH doesn't change much at all by adding that thing. Right? It's kind of weird.